Hello, everybody. Welcome back to one more session. Today, it's our pleasure to have Stanisław Szarek from Case Western University from Cleveland, and Sorbonne University. He will speak to us about generalized probabilistic theories and tensor products of norm spaces. Please.
Okay, thank you very much. In this new world, welcome in the new world. So this is a work which is well, it is a very long abstract, right? So John, I'm not going to tell much about generalized probabilistic theories. So this belongs to foundation of physics, really, and I only vaguely understand what that is really about. Basically, the point is that this is supposed to be like a generalized approach to describing nature, and two special cases of that are classical probability and quantum theory. So basically, it's every framework that describes nature which involves probabilistic elements in some ways also. So that's probabilistic theories. So basically an outcome of an experiment and an outcome of a comes from some probability distribution or from some quantum state, and there is certain level of certain uncertainty. Now the important part of this is how parts of a larger system fit into then the global system, and that's where the fine mathematical points come in. And normally this is being described by tensor product of either cones or of norm spaces or convex sets, and well, we'll go into that. And this leads naturally to some questions about, well, if one wants to figure out what are the possible descriptions of reality, because it's not given that the classical description or quantum description are the correct one, then one may just as well consider all possible descriptions. And then we have it's then when we come into the realm of general norm spaces and maybe general convex sets and their tensor products of all kinds. So basically in the context of okay, so this is, maybe I shouldn't talk about the generalities too much because I will go over all those things in detail. But basically, the bottom line on the mathematical level, we will be interested in tensor products of norm spaces. On the function analytic level, we'll be interested in tensor products of norm spaces. And the two extreme tensor products that are still somewhat natural are the injective and projective tensor product. I'm going to define those, for even though probably most of the audience have heard about them. And then there is a natural question of how much can those two extreme tensor products differ. And we don't answer that question completely, but we give some answers in a number of natural cases. And then there are a few, sometimes even elementary questions sometimes in lower, sometimes in higher dimensions that are open, but well, this is mostly what mathematics will be about: the projective and injective tensor products of norm spaces. And there will be the tools that will be involved will be geometry of Banach spaces and random matrices mostly. So now those questions go back to Grothendieck and Pisier. But strangely, there was no even like a reasonable attempt at quantitative analysis of the problem that was made since then. And I will maybe mention a little bit what was known and what wasn't known. It will sort of follow from the context. So, okay, so now, well, this is the outline. So basically, I went over the outline already. One slide about GPTs, then there will be definitions and notation about tensor products, some history, and then a selection of results. Now on the bottom here of this the current screen, we have the buzzwords from geometric functional analysis mostly that enter. And well, I'm not going to read them. It's sort of self-explanatory, and they will appear not necessarily in that order. Some, so there are some famous theorems like Dvoretzky theorem in the tangible Millman's version, and then some maybe more the famous Grothendieck inequalities. Then the concept of K-convexity, which is maybe perhaps a little bit less known, but it's very useful in this context. And well, star estimate is probably even least known, but for people in geometric functional analysis, it is somewhat known. Okay, so let's move there. So what is the general probabilistic theory? So general probabilistic theory is a vector space with a non-trivial, non-degenerate cone. And then there is a unit effect, which is an element of the dual cone, which is defined as the set of all functionals in the dual which are non-negative on the entire cone C. Now we want that element to be in the interior. So this means that if we, okay, maybe if we look at the inverse image of any positive number and intersect it with the cone, then we'll get a compact set. Now those are all hypotheses here. Now so we have a cone, we have a hyperplane in the same vector space, which is the inverse image of some functional, and that intersection, that compact set, which is the intersection of the cone with the hyperplane, is supposed to represent the states of the certain physical system, which is modeled by this theory, right? So this leads to two norm spaces, in the space itself and in the dual space. And in the space itself is the convex hull of absolute convex hull of the set of states, meaning convex hull of omega, and it's negative. And in the dual space is the order interval between the unit and negative unit. So all elements that are between unit and negative units. So I will give examples in the moment, but the remark about systems and global system is that whenever we combine two subsystems, so for example, like two particles or two objects in general, right? Then the vector space which describes the global system, the combined system, is the tensor product of the two underlying vector spaces. And then the choice of the cone depends on further assumptions. And that depends on our framework of what kind of measurements are allowed. For example, whether, so this is a typical example in the quantum theory. You have Alice and Bob who share an entangled state. and Alice has one qubit of that state, Bob has another qubit, and then they can measure only their own qubit. On the other hand, if there is God, then God can measure the entire entangled state, global measurements, and those different measurement schemes correspond to different choices of cone in the tensor space, tensor product of the two vector spaces. So now, to make it closer to Earth, in the classical case, we have discrete probability densities on a finite set. So this is this gives us a simplex in Rn, and if you intersect it with the hyperplane, which is given, which is implicit in the definition, then you get a simplex, probability simplex of probability densities. In the quantum case, it's a similar situation, except that now we have Hermitian n by n matrices, and the hyperplane with which we intersect is trace-Wien hyperplane. So we are looking at the positive semi-definite. The cone is positive semi-definite cone. So we are looking at the positive semi-definite matrices whose trace is 1. And those are quantum states or density matrices. When you look at the corresponding norms, then the norms are whenever you take the probabilistic simplex and its opposite, then you get an L1, the norm in the L1 space. If you take in the dual space, which will be, of course, the L infinity norm, and this exactly coincides with all functions or all sequences which are between -1 and 1. In the quantum case, we have the trace class norm. So this is the operators whose trace of the absolute value is at most 1. That's the unit ball. And then the dual norm is the operator norm, which is for which the unit ball, again, we are in the Hermitian case. Those are exactly the matrices which are between identity and minus identity. So the unit effect is the identity in the quantum case, and a function, then a sequence equal identically to 1 in the classical case. Now, what is the how does probability enter operationally? So there are measurement of a states give some which are probabilistic outcomes, which are somehow related to the weights which are in the simplex, and similarly eigenvalues of the trace-1 positive semi-definite matrix, which is the quantum state. But there are other schemes which are more complicated schemes, which are also allowed. So you don't absolutely have to measure individual probabilities, but you can group them or even make more complicated schemes in both in classical and the quantum case. But anyway, this is going to be this is sort of like a background. It's not going to play very important role in this lecture, because, well, ultimately we'll be talking about mathematics and not physics. Okay, so going to the norms. So the projective norm is, first of all, on the any all the algebraic tensor product of two real Banach spaces, will consider all norms that verify this simple property here for tensors which are product tensors, and not as opposed to linear combinations of such product tensors or sums of such product tensors. So this imposes certain restrictions. So this is the natural restriction which is necessary. Now, once we impose this condition, then for the by the triangle inequality, every such norm must satisfy the condition, well, here denoted 2. So now if we replace less than or equal by equality, then we'll get the largest possible norm that verifies this original property for any simple tensor, and we get the definition of the projective tensor norm. This is the largest norm on the tensor product of x and y, which verifies this condition that we impose. Okay, so there are various notations for that, and we'll usually write z pi in that case. Okay. Now, what is the smallest reasonable norm? And it's most convenient to invoke duality. So if we want to, so one way to say is that we want a functional, which is a tensor product of two functionals, to induce a norm which is equal. Well, this is requirement for the dual norm, right? Which is at least, which is exactly product of the two norms. So from this it follows that if we take the norm on our base space, the norm of z, so that's going to be greater or equal than the maximum over all evaluations on the product vectors, which sort of like a minimum, well, the smallest possible set of norming functionals. So the smallest possible set of norming functionals gives us the smaller possible norm. And so this is the injective tensor norm, right? Now, this is, well, alternatively, you may think of this as a norm of z as a bilinear form on x star cross y star. So when you apply it to an element of x star y star, there is the usual formula for the norm of the bilinear form that applies here. Well, so basically the way to connect the two is to again invoke duality, and then the epsilon norm can be obtained by passing to the duals, taking their projective norms, and again taking the dual, and of course vice versa, because at least if we are in the finite dimensional case, if the spaces are infinite dimensional, then of course you have to do completions, and there are various issues related to reflexivity, approximation property, etc., etc. But we are not going to get there because we'll be worried about the theory that is local theory. I mean, finite dimensional quantitative theory. Okay, so basically, so the next point is that language of geometric language. So in geometric functional analysis, we often identify norms with their unit balls, and in the opposite direction, whenever we have a symmetric convex body containing the origin, then we can associate with it a Minkowski functional, which is exactly the norm for which that body is a unit set. So instead of talking about norms on vector spaces, we may talk about symmetric convex sets, central zero symmetric convex sets, and this allows us to define the projective tensor product and injective tensor products of such sets. Maybe it's always most convenient to think that they contain zero, because otherwise there are some strange phenomena that may happen. But but in any case, this is well defined for actually for any pair of sets KL, and if we assume that KL are convex and we take the convex solve here, so it somehow leads from convex sets to convex sets, from symmetric convex sets to symmetric convex sets, and so forth. Basically the bottom line, of course, is that the unit ball in the projective tensor product is the projective tensor product of the unit balls, and similarly for injective tensor product. And the way to pass from one to another is to use polars, and which is like, again, basically for morally, this is the unit ball in the dual space, is the polar, but it is defined for arbitrary sets. This can also be defined for other sets, as I said, but most notably this definition makes perfectly sense for cones, and cones are the ones which are most crucially used in the present context, because, well, again, the GPT involves, by definition, part of the definition is a cone. So we have to take cones of tensor products of those cones. Okay, so now there is a very quick, this is just a slide by itself. There is the following simplification, because projective tensor products are a little bit maybe less intuitive, because that they are related to not to the usual norm. What we understand very well is usually when we learn functional analysis, then we learn norm spaces, we learn what the norm of an operator is as an operator between two norm spaces. And so this is like a familiar context. So here of course the epsilon product, which corresponds to bilinear norm of bilinear forms. So by just passing between replacing space X with its dual, we get that such tensor product is canonically isomorphic to the space of operators from X to Y, and we can rephrase every statement about tensors in terms of operators. So here I'm using the bracket notation, or ket-bra notation. So here Z is an sum of rank 1 operators, which consist of first applying functional xi star and then multiplying by vector yi in the space Y. So that's with this identification, with this understanding, the epsilon norm is just simply operator norm from X to Y. Well, so we just have to replace X by X star here in the tensor product. So it's going to be a pi norm, an epsilon norm in this tensor product here. Now, the projective tensor norm is the minimum of all representations of operator Z as a sum of rank 1 operators of sum of norms of those rank 1 operators which are here. And this is, in functional analysis, this is recognized as the nuclear norm of an operator. So we want to decompose our operator as a sum of rank 1 operators in the most economical way, so that the sum of the norms of those rank 1 operators, which are sort of, well, clearly what that norm means, equals is as small as possible. So that's called a nuclear norm, and it's an easy exercise, fairly easy exercise, is that those two norms are dual to each other with respect to trace duality. So the projective norm can be calculated by taking trace of composition of Z with any operator of norm less than 1 in the usual operator norm. And well, this you just have to believe, but it's not very difficult. But this somehow allows us to investigate this ratio, maximal ratio between the projective and injective norm, which we denote rho of xy for two spaces y as a maximum of trace of a composition of W and Z, where W and Z act from respectively from X to Y star and from X star to Y. Now the duality here between the nuclear norm and the operator norm is that you are looking at the operator norm for operators from Y to X and nuclear norm for the operators from X to Y, right? Because when you compose, we have to land in the same space. So that's how those two are connected. So this is just this formula here at the bottom. The second equality, the first is just a notation, and the second is just the fact that the nuclear norm, which corresponds to the projective tensor product norm, and the epsilon norm, injective norm, which corresponds to the operator norm, are dual to each other. And it's pretty straightforward because well, that's how that follows at most from the bipolar theorem for. Okay, so this is going to be very important because it will allow us to basically express everything in terms of usual norms without having to discuss projective or nuclear norms, which are often difficult to somehow, at least certainly I have much less intuitions for the nuclear norm than for the usual operator norm. Okay, so the history, this was studied, tensor products of norm spaces were studied by Grothendieck, well, in the 50s, so that's almost 70 years ago. And he proposed and studied 14 natural tensor norms and posed a number of open questions, some of which became very famous, and then people who solved them became very famous. So in particular, he asked whether it's possible whether that two tensor products actually, tensor product norms coincide for infinite dimensional spaces, and it was I think widely believed to be false. But in the 80s, Pisier constructed a space or spaces, a space for which a pair of spaces, well, it was actually the same space even, which were on which the two tensor products were equivalent, and that was a purely infinite dimensional phenomenon because he earlier showed that in the finite dimensional case, if you have a sequence of two sequences of spaces and then their dimensions go to infinity, then the ratio of the projective tensor products, of the maximal ratio between the projective and the injective norm between those spaces must go to infinity. So there is this big disconnect between the finite dimensional and infinite dimensional case. Here we'll be only working with the finite dimensional case, and somehow strangely, no one since then really looked at how that quantity rho depends on the dimension, and even for relatively specific spaces. Okay, so here maybe let me do a commercial for well, some of my co-authors really who considered a similar question for cones, and this is in finite dimension. So when does it happen that a projective tensor product of two cones coincides with the injective tensor products of the cones? Now, as opposed to the norm spaces, it's easy to check that if one of those cones is classical, which means that Rn plus to some power, and the other is arbitrary, then those two are actually equal. This may be a little bit surprising and somehow look, because somehow how come the nuclear norm and operator norm are the same? But this is not really norm. This is a very special property of the simplex. Well, what we mean here is that classical means that it's isomorphic to standard cone, which means that it's spanned by in Rn n half-lines, and which are like correspond to the half-axis. Okay, so now this is 3 of my co-authors with someone else who Plavala, who proved that. So this is a very elegant result, and it answers a problem that was around for something like 40 years or more. So now this may seem, maybe let's go back a moment. This may seem like somehow like, well, this is just one more characterization of an infinity space of L1 space, but there is, I point out there is a very fine point here, which is that we don't know which of the two is classical. Right? Just by whenever we have this equality, then we know that one of them is classical and the other something, but we don't know which. So it's clear that there is a little bit more in the problem than just a characterization of the L1 or an infinity space. Okay, so now let's talk a little bit about some special cases. Now, how much time did I cover up to now?
You still have 20 minutes at least.
20 minutes. Okay, so I better hurry, right? Okay, so the situation is very simple if you have 2 Hilbert spaces, because in that case the operator norm, we have operator norm and spectral norm, which is sum of singular values and maximal singular values. So this is like an L1 and L infinity norm. And so the ratio is if it's the same dimension, the ratio is exactly equal to the dimension, because L infinity norm and L1 norm ratio between them is maximally equal to the dimension. And if the dimensions are different, then it's the minimum, and it's very easy to figure out. And actually this is a easy general upper bound for rho of xy. So this saturates the general upper bound. For a general lower bound, one could naively try to do John's theorem and use the fact that every space is within square root of n of something of the Hilbert space. But however, it is easy to see that while you can get some non-trivial result. So for example, if you take one of the spaces arbitrary and the other is a Hilbert space, and let's say that they are both of dimension n for simplicity, then we know that x is within square root of n of a Hilbert space. And if we have two Hilbert spaces, then the distance, well, then this quantity is n. And so, well, it's pretty elementary to show that in that case it's going to be this. It follows that from John's theorem that we have at least square root of n. However, we cannot. This doesn't work well. While this allows handling spaces of different dimension, not necessarily both of dimension n, this doesn't allow to do anything in the general case, except for the Qt equality that rho for xx star is equal to the dimension. Because the problem is that whenever we have 2 arbitrary spaces, then each of them can be at the distance square root of n to the Hilbert space, and moreover, they can be at the distance n among themselves, and there is no way to infer any non-trivial lower bound from this circle of ideas. Now, but however, there are some interesting special cases that can be handled. So for example, if one of our spaces is L1n or L infinity n, then and the second space is arbitrary of dimension at least n, then it's not difficult to show that the discrepancy between the projective and injective tensor product must grow as fast as square root of n, and specifically we have a bound which is square root of n over 2 in both cases. And those are actually equivalent, because it's easy to see that whenever we take two spaces xy, then rho for xy is the same as rho of x star y star. So if we have this with full generality for arbitrary x, so we can just by duality we can get the same result for L infinity. Now this is not absolutely trivial, but it follows by relating the discrepancy in the tensor product with L1n to p-summing norms of the identity on X. And I'm not going to go into details, but this just can be related directly as an equality of some. This ratio here can be rephrased in terms of some absolutely summing norms, and those are reasonably well understood, and that's how all this follows, right? And then the remark is that you cannot give an improvement to this that works always, to this estimate, or at least substantial improvement, because if H is a Hilbert space, then it's easy to show that the discrepancy between H and L1n is exactly square root of n. But we do not know whether for every x you can get a lower bound with square root of n when the second factor is L1n or L infinity n. Okay, so anyway, some special cases can be easily calculated or fairly easy. Now, another case that is a specific case that can be figured out, though not as easily, is the case that it's relevant to quantum theory, which is when the two spaces x and y are spaces of Hermitian matrices endowed with trace class norm, which is those are exactly the spaces which appear in the quantum context with quantum states and positive semi-definite cone and so forth, right? So in that case, the result that we get is that the order of discrepancy is sort of in between what happens in the case of Hilbert's n-dimensional of the case of Hilbert spaces and what happens if one of the spaces is L1 and the other is a Hilbert space. And namely, we get the dimension of smaller dimension of those two spaces to the power 3/4, which sort of is maybe believable, because those spaces are in some sense, trace class norm spaces are in some sense mixtures of L1n, L infinity n, and so, well, they are somewhere in the middle. But however, the argument is not completely trivial. So let me just a few words about the argument. So this is this is a probability analysis webinar, so there will be some probability, and the lower bound is obtained by using random tensors. So we just take any orthonormal basis with respect to the Hilbert-Schmidt inner product in the space of Hermitian matrices. Now, if those were arbitrary matrices, right, we could just take the basis elements, Eij, right? But since the matrices are supposed to be Hermitian, we can take Ejj for the diagonal elements, but for off-diagonal elements, they have to be self-adjoint, so they have to be either symmetric or complex anti-symmetric, and that's how we can construct the basis, right? basically some kind of a Pauli matrices, if that tells you anything. And GJK are independent n of 0, 1 random variables. And we use this Z to test the norms on, well, basically to test the ratio between the pi norm and the epsilon norm. And for that, to that end, we use this formula, which is the maximum. This is, I just rewrote the formula, which is rho. This is maximum of the trace of the composition of operators whose norms between y and x star, well, again, x and y are those trace class spaces. And specifically, we do W is the transpose of Z, right? So that's how we create well, transpose of Z here in the composition. So so there is no mystery whatsoever what the ZTZ is, because this is just the Hilbert-Schmidt norm squared of the matrix Gij. So this is the chi-square variables with d squared degrees of freedom. So it's absolutely clear what that is. But for the norms of the operators Z and Z, with Z and Z and ZT are essentially indistinguishable, because it's just exchanging the roles of the two spaces xj and yks. So they can be the well-known since the 70s way to evaluate norms of Gaussian matrices is using the Chevet inequality or Chevet-Gordon inequality, which has slightly better constants. And that's how it goes. So I'm not going to give further details. I will mention Chevet-Gordon inequality later if I have time. For the upper bound, maybe I should do it very quickly, because just to give you an idea about where it comes from, and it comes from the non-commutative Grothendieck inequality, because every element which is in the injective tensor product of two spaces can be thought of as the bilinear form on the product of dual spaces. Now, in our case, if x and y are trace class, you have trace class norm, the dual has the operator norm. So in other words, we are talking about matrices with operator norm, which is a C-star algebra. So the version of Grothendieck inequality for C-star algebras applies. And this means that there are states on A, which is the space of matrices. And what are states? There are states as functional of norm 1, which are 1 on the identity and which are positive in the C-star algebra sense. So in this case, this coincides with quantum states, right? Because those are the positive semi-definite matrices with trace 1 and positive semi-definite matrices with trace 1. That's it. So with this information, knowing that there is this phi psi, which are just trace 1 positive semi-definite matrices in the proper sense, in the proper space, we have such an estimate for Z. We want to estimate the nuclear norm of Z, and this is done in the following way. So maybe, well, I probably don't have time, so let me just flash the entire slide almost at the same time. So the point is that we focus on one of those two states, and that's a state on n by n matrices. So this is a n by n matrix, trace one, self-adjoint, trace one matrix, semi-definite, positive, semi-definite. So the eigenvalues are non-negative and sum up to 1, and it gives us certain matrix, certain basis, which is which is distinguished by that decomposition. And then by using those lambda i's and that matrix UI, we can cook up a decomposition of the operator Z in the sort of like the most obvious way by looking at the rank 1 operators, by using the matrix elements associated with that basis UI as rank 1 rank 1 as sort of like the seeds for the rank 1 decomposition, right? So this is, I'm not going to say more because I probably have like 10 minutes, right, or less, right? How much time do I have?
Yes, you do have 10 minutes.
Oh, yeah, okay. So basically, if we don't cheat, it's going to be another factor 2, and the cheating somehow involves that there is some real part and imaginary part that has to be considered separately. Okay, so here are the results in the general case, and I'm not going to be able to say a lot about the arguments, but this is those are like the main results in a way in our paper. So if you have two copies of the same space, right, then the distortion or the discrepancy between the projective and injective norm is essentially square root of n at least, right? So in some cases, of course, it's n, as in the Hilbert space. In some other cases, like in the case of L1n, it's going to be square root of n. But in this case, when they are both the same, it will be always the square root of n modulo logarithmic factors. So this is almost optimal, right? If you have two spaces which are of the same dimension, then you have the power that we get is 1/6. And if we have two spaces of possibly different dimensions, then you get 1/8 power of the smaller of the dimensions. Just to put it in the context, somehow when we started working on this, then we asked Gilles Pisier about what his argument gives for quantitatively, because this wasn't stated at all in the paper, but you could somehow extract, and he went back and he looked. And so in this case, whenever you have two identical spaces, if I remember correctly, his argument was giving n to 1/10. So it was power order, but far from optimal. And it didn't really give anything reasonable in the case when we had different spaces and different dimensions. Okay, so a little bit about optimality of this. So somehow, we know that the best things that one can hope for is in all those three cases is 2n to 1/2, n to 1/2, and n to 1/2. And we know that the 2n to 1/2 is not sharp, but we cannot don't know whether the factor can be entirely removed. And it is conceivable that all those quantities are actually of order square root of n. So this is an open problem. We're able to get the power type behavior, which somehow makes all complexity people happy, because this gives well, one gets into polynomial hierarchy, and there is no only different power, different exponents, so that's fine. Also, it's interesting to know that we're able to show that if the spaces are two-dimensional or higher, then the discrepancy is always at least 19/18. So this means that as long as the dimension is greater or equal than 2, there is no way for the norm spaces to have identical injective and tensor product, and when we have this separation, strict separation from 1, and actually we can show that it's at least 8/7, but we didn't include that in the paper because it includes some. It was actually a numerical argument involving a number of steps, and we suspect that actually square root of 2 is probably the right number. So that's another nice problem for even for an undergraduate student, maybe. So I have like a few minutes, right? So just a few words about what is the toolbox in the general cases, and this general case is fairly involved. So basically, maybe let me bring the entire page here. So here I'm just repeating the formula for calculating these discrepancies. So basically, always whenever we want to lower bound this, we have to exhibit operators from a space between some pairs of spaces, which are bounded, but the trace of the composition is large. Right, so there is no surprise that that's possible. So in particular, this explains completely the fact that, which I mentioned before, that whenever you take x and x star, then you get n, because you just take w equals to z equals to identity, and trace is of course n. So this is all that is behind that remark. And then one applies appropriate relaxation of this invertibility condition here, which would give normally trace n. And the way this goes is that so basically, what's the idea here? The idea here is that just we want to reduce the problem in general spaces to problem in known spaces, right? And the way this quantity can be controlled is if, for example, if we can represent one of those spaces as a well-complemented subspace of the other, right? Because this somehow corresponds, this sort of like corresponds to the situation when we have when the composition of two bounded operators is identity on a smaller subspace, which has large trace, right? Basically, does that. So then one can define the weak factorization constant, which is the same formula, except that we allow convex holes. So we represent this composition, which is identity, as an expectation of compositions, and calculate the expectation of the products of the norms, and this allows us to give a probabilistic argument, somehow a probabilistic, well, based on calculating expectation, the lower bound, this formula here, because ultimately there will be a trace of identity, which will give us the lower bound. So here further I list like the obvious, the invariance properties which this has. So whenever, well, first of all, weak factorization and the usual Banach-Mazur distance are related by those inequalities, and essentially from pretty much almost from the definition we get that if we control weak factorization between the two spaces, then we also control, which is not symmetric, maybe I should emphasize, then we also control the discrepancy on one of the space with respect to arbitrary factor by the discrepancy by the other space with respect to the arbitrary factor. And so this gives this lower bound in terms of the discrepancy in terms of the weak factorization constants, and this is connected to the concept of weak distance of norm spaces, but I'm not going to go into there now. So maybe do I have any minutes left?
Yes.
How many?
We're over time, but you can go on.
Okay, so let me okay. So very quickly is that if certainly, well, if two spaces are the same, we just select the two operators U and V at random. It's very similar to what I described in the case of the trace class spaces, and the only fine point is to properly find the proper Euclidean structure, and that proper Euclidean structure is given by the so-called MM star estimate, which tells us that the width of the set and its polar are simultaneously controlled. Mean widths are simultaneously controlled, and mean widths it's something that is very closely connected to Gaussian means of regular of standard Gaussian random variable on the space, and well, in this case of its dual. And okay, so this well, so this is Chauvet-Gordon inequality, which contains exactly those terms, and those terms can be factored, can be controlled by using the so-called this M position, which allows to simultaneously control all those quantities in certainly those two quantities in this space and its dual. So here this is about MMM star, and this is the result that we are getting, right? In the case when we have two spaces of the same dimension, and here I say what it means, what is the M position. So basically, for those of you who know what the mean width of a set is, the MM star estimates somehow that after appropriate change of choice of scalar products for any convex, centrally symmetric convex sets, the mean width of the set and or this rebalanced set and its polar product of them is at most log of n. This is a very useful estimate. The trivial lower bound is 1 here, and easy upper bound is like square root of n, and that which follows from John's theorem. And the result is that we are getting this this bound, which is this logarithmic factor up to which the square root of n estimate is true. Now I'm almost on the last page, so maybe let me give the entire. I didn't plan to give the entire argument for x different from y, but the strategy is to reduce the problem to known spaces. So there is a trichotomy. An arbitrary space contains either a subspace, reasonably well complemented subspace, a subspace which is reasonably close to L infinity of some dimension, and then that subspace is also reasonably complemented necessarily because L infinity is always complemented. The same is true for the dual, or the same is true for the dual, in which case our original space contains a reasonably well complemented subspace, reasonably close to L1D, or the same is true for Euclidean space. And then there are some parameters with which one optimizes over the parameter A, which is a priori arbitrary, and one gets a bound which was given for in that case, and that depending on whether the dimensions are the same or different, it works differently. But that's how this roughly works, and that's it. So thank you.
Thank you very much. Are there any questions or remarks? I have a question. In the non-balanced case, you said the bound is n to 1/8, and you don't suspect that it's optimal. Is this because of the trichotomy?
Well, you see, the argument is the trichotomy, goes through this trichotomy, and which is reducing the case to something that we know, understand, and we know, and there necessarily we are going, those objects that we identify in an arbitrary space are going to be necessarily of substantially smaller dimension. And so somehow this is, well, those are, well, you are going through something. This is like if you are trying to prove something about arbitrary space by approximating it by the Euclidean space. Mm-hmm. Right. So of course, this is a very rough argument, and some things were going to be totally false. And here we are not approximating just by Euclidean space, because that would be the naive argument from John's theorem. We are using 3 test spaces on which we know how things behave, and we are sort of optimizing between all possibilities that that may occur, and in the process here we are losing something, because we are, yeah, it's quite clear that this is not optimal, right? Mm-hmm. I would be really shocked if this was optimal. On the other hand, where I'm not convinced that the answer is actually square root of n. Maybe it's 4th root of n. That would be somehow conceivable, right? Because okay, there may be some kind of symmetry that can be exploited, but this is well, of course, the argument goes through by approximating things which we know that are not really very good matches in general case.
Okay, thank you. Any other questions?
Oh, I was just curious about the square root 2 for arbitrary 2 x and y for the lower bound. You said that you suspected root 2.
Well, we think that this is true for all of them.
And where's the root 2 come from?
Square root of 2. Well, okay, so when you take L1, when you take a square and a disk, you get square root of 2.
Ah, okay.
Yeah. So that's that. On the other hand, if you take the space and itself with itself, you get 2. That's an example of what. No, if you take square and square, you get 2 because square is the same as its dual, right? For example, right? And so in many cases you get but and we were, well, so yeah, but we were not able to come up with a very good argument that would really give chances for being even close to optimal. Then, for example, if you take a space whose ball is a hexagon, you get also 2. Right, so that's even for well, with itself, because it's self-dual, right? So for all spaces which are self-dual, you get 2. So, but
okay, thanks.
Yeah, but this looks like a neat problem, which I think you can even give to a student, to an undergraduate student. It's just about 2-dimensional shapes.
Any other questions? If not, let's thank our speaker again. And we'll see you hopefully all next week. Thank you very much.